11, how are we doing? Yeah, 11:10. All right. All right, folks, welcome to CS10 BJC Lecture 5 Programming Paradigms. Woo! So, today we always have a computing the news, and what we've got is, here's the slide that might look exactly like last time's slide. Turns out that these researchers, I believe they were at, I blanked where they were. Let me see. Georgia Tech. Sorry, thank you. Georgia Tech. They have invented a really amazing keyboard that records force. For every key, records force. And it also records the timing between the keys. And so they ask these users to type things, like type, hello, type your name, type things. And then it turns out that there's a signature from the way people type. The force they use for each key and the timing between the keys. So then what it means is your system could know who you are and no one could use your computer. Isn't that cool? So if someone gets your laptop, they know your laptop knows how you type and you can have it setting so it's only ever you using your computer. Is that amazing? You don't have to log out anymore because somebody else tries to type something and nothing happens. It's like, wait, hey, I know how you type. This is not you. Isn't that kind of cool? So, that's a really wonderful, it's just a research prototype, but it's kind of neat to be able to figure that out. They developed this intelligent keyboard. And now here's what's fun. Ready? Watch this. This was today's slide. This was yesterday. This is Monday's slide. Ready? See? Same theme. Your coding style gives you away. Your typing style gives you away. It's a lot of interesting things. These fingerprints of how you go through your life, typing on something, coding things. It's kind of interesting how those are used to be able to figure out how you are for good reasons. Almost all these are good reasons. This is to resolve plagiarism, malicious code, and today it was about not letting somebody else use your keyboard, and even if they had your password, they couldn't actually use your computer to do that. So it's kind of cool. All right, so now we're back to here. Starting Eric, give me the thumb over here. Eric, programming paradigms. All right, 3, 2. All right, welcome back, folks. Today we're going to be talking about programming paradigms. And programming paradigms are the style you use to program. So we'll learn a couple of those today. So formally, this is the definition of that from Wikipedia. The concepts and abstractions used to represent the elements of a program, for example, objects, functions, variables, and constraints, etc., and the steps that compose a computation, assignment, evaluation, continuation, data flow. All these are complicated words, but it means the style you use to program a computer. And most of you have only seen the way we're programming a computer, which is through Snap, so it's hard for you to kind of get a sense of other ones. So today I'm going to try to share with you other ways that you might want to be able to program a computer. The style is the paradigm. The first is a functional model. And this is, again, the third time we've seen this slide. This is all a review. We're talking about the world is only functions that have inputs and a single output. And you compose them together in clever ways. So here is this function f that you're trying to write, and itself it's written by composing other functions together. So I'm going to borrow the plus function and the square root function and the multiply function and then feed the data like this in this way. What I've added is on the bottom corner, you'll see the code that actually embodies that function in Snap. So you can think of that as being this picture where data flows like this, or if you just think about the expression that Snap is, that's a little easier. Okay, so that's functional models, again, very standard. We've seen it before many times. And remember, no state, no side effects, and no mutation. Those are the three things, okay? Same input, same outputs. All you've seen before. Ooh, new idea. This is called imperative programming. And imperative programming is like a recipe. The picture I've shown here is because I think of it like a recipe. First, break the eggs. Then scramble them, then add some chives, and then put them on a pot. And then so it's all these steps. So it's called imperative. Another word for this is called sequential. So it's a sequential nature. You're doing one after the other, after the other, after the other. So if you were to try to recreate that same function over here, so f of x equals x plus 3 times square root of x, the way you could do that is by saying, here's the procedure right here, f of x. Answer equals x. Let's just start with answer. I'm going to return an answer. But I say answer equals x. Uh-oh, there's an equal sign. Already we're not functional because I've used an equal sign. You're not allowed to have an equal sign in any assignment in a functional model. So assignment, all of a sudden you know you're out of the functional world. Answer equals x. So we start with the answer. I'm going to return answer. So I'm going to give you at least x back. And then if I say answer equals square root of answer, what does that do? Well, that says that now it's the square root of x, because remember, answer was x a second ago, so now answer is square root of x. So I'm working my way through my computation. Answer equals x plus 3 times answer, and now all of a sudden I'm done with my computation. If I return answer, I'm returning the quantity x plus 3 times square root of x. So that's kind of a way to have some assignments, some stages, and you might think about why, that's the reason why we can't parallelize imperative and sequential programs very easily, is because you have these stages, and these stages all have, what's the word to say? The stages all have kind of a step. You can't just say, well, I've done 4 steps to do my algorithm, and they can't come out of order. There's a particular order that's required. When you send computation to many machines, they come back out of order. Because that machine's faster, the network is slow there, the disk is really slow there, that machine's bogged down with computation. So you have to be able to handle work out of order, which is why functional stuff is so beautiful, because there's no order to those things. In the flow, I'll go back a picture. In this flow, it didn't matter whether the square root happened before the plus, right? Think about that. Here's the flow of the data through that kind of a box. It didn't matter which happened first. At the end, the time's going to wait for both of those to be ready, and when they're both ready, they'll come out and do the right thing. Didn't matter whether there's an order here. But look at this stage. Look at this answer equals answer. If you send each of those lines to a different machine, you can't have them come back and it doesn't make sense. You needed the results from the earlier step to be able to work with the next step. So you can't parallelize sequential or imperative programs as easily. You can do it in little limited cases. All right? So far what we've seen is an introduction to what the idea of a programming paradigm is. It's the style of programming, the style of taking your thoughts and embodying them in code. We've seen the functional model. We've seen the imperative model. All right? Next video, we'll talk about 2 more models. Thanks. Okay. Off. Any questions we've got now before we go to the clicker? Okay? So I've seen 2 models, a review and a new idea, imperative. Okay? Here we go. Let's hit our clicker now. Bink. And clicker. Yoink. And say this. And say start. I'm going to close this door because I'm hearing a lot of door closing. Eric, remind me in the future to close this door before I start because I'm not closing the door and the people are making a lot of noise coming in. Okay. Here we go. Okay. And action. Okay. Action on what question? On this question. Yoink. Okay. Which of the following is true? Functional style code is actually imperative style code. Imperative style code is actually functional style code. Both A and B, neither A nor B. And action. Ooh, I got a nice spread. Very happy. Yes, yes, yes. I actually gave up. This is a question I was going to have on your midterm. And I actually gave it to you for free. So there we go. How about that? Okay. But good spread. I love it. This is making me happy. Excellent. 160. And we're still moving up slowly. And stop. All right. This is a good spread. Talk to your neighbors. You're almost evenly distributed. Go. Figure out what that answer is. What's the deal? Make sure to know the name of your neighbor. Make sure you know the person's name. Introduce yourself if you haven't done that. All right, let's come back. And vote. You and your neighbor have to have the same answer. Vote again. Go. Okay. How's it coming in? Let me see if you guys have changed. Wow. This is really good. Boy, Michael, make a note of this. This is probably the best question in terms of spreading them out. You folks this is delightful. This is great. Where's a Florida? We need Florida to like tip the thing over here, right? All right. Here we go. 140, give me 160, people. Love it. Oh, I'm sorry. Okay. Ready? Stop. Okay. And now look at this. Huh? With the thing? Here's your first one. Isn't that very interesting? And here is your second one. Now, I think there's a case to be made for all four of them. I'm not saying that's the right answer, but who voted A? I've got how many people I have? 25 people. I need somebody to say, like, come on, this is the answer for A. And I want to have people discuss. So be brave. Be brave. I see a waving hand. Okay, waving hand. He's calling his friend over. I'm just hoping. I'm trying to get him. I'm trying to bust him for the A. I need an A. I need somebody who's brave, and wants to argue A. 25 of you voted A, so I need somebody to say that. Yes, go. Oh, come on, he's my TA. Come on. Give me some love on the A team. Nobody on the A. 25 people. Yes, in the back. Tell me your name. Studi, go. Right? Functional style evaluates different functions. I'll repeat because people can't hear you. Yeah, go ahead. And imperative is steps, right? Okay. Functional style is kind of following steps like imperative code would. Great. A. Give me a B argument. I'm not saying right or wrong until the end. Give me a B. Come on. This one was a big one. 44 of you. Come on, give me some love. Thank you for being brave. Come on. Yes, good. Tell me your name. Ishan, go. Yeah, I'll walk over here. Watch your left. Go ahead.
So with imperative style of...
No, I'm busted. Go ahead. Imperative style. I'm just having fun. Go ahead.
So imperative style code, with the idea of sequential programming, seems like you are applying a function and an additional function in sequence.
Okay. So it's like functional, but it's in sequence. Interesting. Okay, I like it. All right, B, good. Give me a C. Give me somebody. How many of you? 27 of you. Looks like said both. So give me some love there. C. It's a really good question. I'm glad that I asked this. Last night I was like, let me ask a question about these two and the relationship. C. Come on, we got to have two good arguments for A and B. And give me a C. You could just say what they said. Come on, just so you say. Nobody for C? How about D? Go ahead. Tell me your name. Bar. Go ahead. Imperative is by sequence, right? Function doesn't be by sequence. Oh, it's either A or D or neither. Okay. Okay, great. Okay, 4 good answers. Okay, let's assume the C person said A and B, but they said they're right. Okay. So now, let me ask you a question. I'll just ask you one question. Did I tell you functions you can't have assignment, right? Did I tell you, if I had done this right here, let's close this for a second and go back to here and look at this expression right there. Okay? Is that expression at the bottom right? I'll zoom for you and see if I don't know if this works on the webcast thing, probably not, but let's see. Is that a functional style coding or an imperative style coding? We know it's at least functional because I put it's a functional slide. But is it imperative style also? It is. You don't have to have assignment. You don't have to have mutation. You don't have to have state change to be imperative. You can. It's like more expressive. It's a larger thing, but you can have purely functional and be imperative. So the answer, back to it. I closed my thing. So the answer that I say on this question is functional style is really imperative style. Right? You don't have to have assignment. If you live in a functional world, you're still an imperative world. But the moment you have an assignment, then you're no longer functional. But functional is really a smaller set. Imperative is a larger umbrella. Does that make sense? Agree? Pretty cool, huh? And it's almost the smallest number. Okay. Congratulations to the A folks out there. Good job. Okay. So let's go back. I'm going to take this. I'm moving this thing, Eric, to the top of the screen, which I'm going to replace it with the thing. So I'll leave it up there running, so I don't have to keep booting it and closing it. All right, let's come on back. I'm going to teach you object-oriented programming, the third type. All right? So I'll wait for my thumb up. All right, 3, 2. All right, folks, welcome back. Now I'm going to teach you the third style, which is called object-oriented programming. So this is also known as OOP, and you may have heard this before. If you've heard of the language Java or C++, which is on the bottom, some examples. These are examples of object-oriented dominated programming. The idea is the following. Everything in your program is an object, okay? And they are data structures. They're where you contain their data. You have each object, for example, what do I have here? For example, a pianist. A pianist. I have a simulation of people running around, and one of the examples is that somebody plays piano, okay? So that person has their name. They have the ability to play piano. So I could ask of that person, please play a concerto, and the person starts to play concerto. It's like I'm hiring them in some sense. So I could say, walk around the room, and they walk around the room. So each of these objects has methods that you can ask them to do, things that they know how to do, right? Just like somebody you're paying to clean your house. You could say, clean the windows. They clean the windows. You clean the floor. You scrub the sink. Pianists, you can ask other things too. They're different, right? Different objects might have different methods of what they can do. Each object also has properties. We call that local state. So each object might have things about itself. It might have their name, so that name might be in common, not the same opposite name, but both a pianist and a house cleaner might have a name, might have abilities to have a name. But the piano person might have local state is the number of songs they know by heart. House cleaner doesn't have that kind of thing. That's not there. They can play by heart on request. House cleaner might be the kind of chemicals that work really well on getting a stain out of a sink. Piano person knows none about that. So local state is like a local set of information that each object has. You have classes and instances. The idea is you make a factory. This is a piano person maker. And I turn the crank, and out comes a piano person. Turn the crank again, out comes another piano person. Each of these things are different people. That might be, I might assign a random name to them all. So I write a random name from the alphabet, random name from the list of baby names. Crank it, here's Al, the piano person. Crank it again, here's Susanna, piano person. I can keep cranking it and getting random names. And these are different objects. Okay? Then, you also have, so the factory is like a class, and I turn the crank and I get instances, a particular instance. So Al and Susanna are two instances of objects that are not the class. The class is this factory. Okay? Inheritance is a really powerful idea, and inheritance saves us reducing code. Remember how annoying we were back in the day when we were looking at functions, and we said, look, here is move in turn 4 times, but move 100. This is move in turn 25. This is move in turn 395. And it's like annoying to have 3 separate pieces of code that were basically all draw square with different variables. We want to have generalization. Well, you end up having with big object models and big object source code, you end up having things that are in common. For example, both the piano person and a house cleaner both go home at night, and both have the meal they just ate, and both have parents and children, and things that humans have, and things that employees have, like, tax ID numbers. They each have a tax ID number and a field in their local state for their tax ID number because they're employees. And you end up realizing the code that you have, which is like file tax, that you have for both the piano file tax and the house cleaner file tax are the same thing. Why do you have the same code how to file tax? That's just a people thing. That's not about a particular to the piano person. So you end up having these hierarchies. An example I gave is a pianist is a special case of a musician, someone who performs music for a living. And a piano is a special case of that. A musician is a special case of a performer. Performer might be a special case of an employee, which might be a special case of a human, okay? Which might be a special case of a mammal. Right? You keep going up the chain. Which might be a special case of a living thing. So this huge thing allows you to isolate the code about something. Where would you put the code for doing taxes? Well, you wouldn't put it in mammal, because not all mammals do taxes. You might put it in human. Or maybe employees, because not all humans are employees. My kid doesn't have a job. He shouldn't have the tax code in him. It should be an employee. So you can isolate the code and have it exist once in the tree in a really cool way and have the code to do taxes only in employees. how to play the piano perfectly, how to tune and make sure the piano's tuned is on the piano, because you wouldn't put it under musicians. A trombonist wouldn't know how to tune a piano. So it's all about the special case or code that's relevant to that particular class of things. It's really cool and reduces, when you have a really complex system or simulation, it really reduces where repeat code lives. It's really very, very nice. People who work with inheritance love it in terms of isolating where stuff lives. So each object knows about itself, knows about its local state. Each object knows the methods it can do, and it reveals the methods it can do, like play piano, tune piano, clean a sink. And it exposes those people who then can ask it questions. Say, here are the things you can ask of me. I'm a piano player. You can ask me to play a song. You can ask me to walk around the room. You can ask me to file my taxes. That's all I know how to do. Okay, house cleaner might say, I know how to clean a window. I know how to do other things. So you would share things that are your methods that are exposed to the other world, and you have those methods isolated in the inheritance hierarchy. A lot of new words for this. This is hard. You'll often see this in your second class for majors at a university. So if you follow up with this, you'll do this. Or if you're taking the AP Computer Science A exam, you see those issues when you're learning Java in APCSA. So I'm now going to show you an example, probably the most amazing example of an object-oriented programming code base, which came years and years ago by a wonderful man named Dr. Ivan Sutherland. And we had the great fortune of having him come to Berkeley for several years. He is known as the father of computer graphics, which is awesome. He invented the field of computer graphics. People often say this video and his thesis at MIT was the beginning of computer graphics. So I'm going to show you object-oriented programming, but in a visual way, and you'll say, oh, I get it. What's an object? What's a class? What's a factory? What he uses, by the way, is a different style, subtly different, called prototyping OOP. And prototyping OOP is a little different than the classes and factory I talked about, in which any instance can be itself a factory. So I have an example here of a particular shape, and I can say this is a factory, make copies of it. And then if I go back and change this one, these guys are like my children, they'll change as well. It's called a prototyping. So it's like the prototype, I can make those. And these can be prototypes. So it's a little bit different flavor to OOP. Okay? So, and I'm going to see, we'll come back to, after I show you the video, we'll come back to this one. It says it's the first object-oriented system ever. It's the first graphical user interface, and it's the first non-procedural language. Non-procedural meaning a graphical language rather than a normal text-based procedural language. Okay? So we do a little quickie video check, and then we'll come on back. All right? Good. So now I'm going to go to the video and show you. I think I have to stop the recording. Okay? All right, let's come on back. Let's try it. 3, 2, 1, vote. Here we go. Remember, you guys, you and your partner, whose name you now know and you're friends with, and maybe you're going to be thinking about partnerships for that friendship you're making a lecture is going to evolve to working together, studying for exams, and we're trying to make the class a little smaller. 26,000 undergraduates, it's easy to get lost in the numbers. So, yes? That's a good question. So there's a question, as you're voting in, there's a question, is an object like a branch of a tree? In some sense, in the prototyping model, the one that you saw, the flange can make sub-flanges, yes, it is, because the master copy can make sub-guys, and so wherever you are is wherever you are in that tree of prototypes. In the factory instance, it's less about that. But it is still, the factories are still part of the tree of inheritance. Remember, the factory of piano makers is under, in some sense, the factory of musicians, which is under the factory of performers, under the factory of employees, under the factory of humans, under the factories of mammals, right? So in some sense, both of them are like, that's true. You can think of this tree as relevant in both of the models of the OOP. I like it. Well done. Well done. Okay. Wow. You guys didn't move at all. Okay. I'm closing out. 3, 2, 1. Look at this. Fascinating. So isn't that great? Here's 3, and there's 4. So you lost some A. A's went away and became E's. All right, we can go with the E's, That's what I did. So, what's really interesting, let's think about this. Can they delete or not? Basically, this is a bit. Look at this. These are 2 questions I'm asking you. And each of them is like a bit. 2 bits, 4 possibilities, that's why it's A through D. Get it? I'm connecting with the bits and all right. So, is it like off, on, off, on, on? Okay, so there's 2 independent questions. Can they delete other objects? What do you guys say? So the people who say delete are the A's or no, and C's. So basically C says yes. So delete is interesting. They can't, they're all independent, right? They can't technically control an object. But what I can do is send a message to another object and say, delete yourself. You see? So if the object says like, zoop, and it just evaporates, then I could actually send a message to you and say, zoop, and do that. So in some sense, I say yes to that because I could pass the message and say, go away, and then I'll just go away. Right? So the answer is yes to the A question. So now it's either A or C. Right? So now, looking at C, how about contain? Can it contain or not? Well, here's the cool thing. Each object has local state. Within their local state, part of the thing local state could be a big list. Like, remember I told you there's a list of songs that I know, that the piano player had? Why couldn't I have list of my friends? And my friends are other objects that are in my list. Right? You have a list of phone numbers of your friends. Why not have the list of friends right there? They're directly. Here's my 5 friends. Bam, I can do them. And for each one of them, call them. Send a message, call them. Wish them happy birthday, whatever. Okay? Wish them hope you survive the snowstorm. Okay? So, okay? So they can both contain and delete. So therefore, C's got it. Well done, C, which has the higher number. Okay. Good stuff, right? Okay. So let me do a quick time check. Great. 10 minutes. We're going to see the last one, then close it out. Okay. Here we go. Okay. Coming back. Okay. Fun, right? Isn't it kind of cool? Interactive with the thing? 2 good questions. Okay. These questions, by the way, could have been on your exam. These are really good questions that were exam-level questions. I decided to give those away for free as a gift to you, okay? To give you a sense of what we ask on exams, okay? And, all right, 3, 2. All right, welcome back. Now we're going to see the 4th style of programming paradigm, which is called declarative programming. And declarative is the coolest, most wonderful magic of the 4 that we're looking at. So declarative has the idea that you don't tell a program what to do. What are all the other programming languages, paradigms? They are do this, do this, do this. Okay, maybe it's send message there, receive message, do something, right? Declarative is like magic. Declarative, you program in rules about the world, rules about the system, and then you query the system, and the system tells you answers. So it really is, if you think of this beautiful cross line, it's much less telling it how to do something and more what I want. See the crossover? So declarative is much less how, it's about the what. And the opposite is imperative, where it's mostly about the how to do it, and only if you kind of step back and really look at the code are you seeing actually what it's doing. Okay? So imperative is more about the process, and declarative is more about the answers and the results in a kind of a cool way. So here's some great examples of declarative programming. I might put in all the facts about my family, okay? Your whole genealogy tree. And then you ask it, what are the names of what are the names of all my second cousins? Boop! It just tells you. I didn't tell it how to walk the tree. Okay, if it's equal to second cousin, add to a list of the names returning. No, here's some facts. I say, who are my second cousins? Boom. That's amazing. I might ask it other facts. Like if I put in other facts about the world and the system, I might ask it facts saying, find me, if I have a car that can hold 1,000 pounds, and I have the weights of every relative, I say, find me the relatives who would perfectly get closest. If I had 4 people in my car that can hold 4 people, get closest to 1,000 pounds. That's a lot of code to do that. Well, go through each of the cases of 4 and look at the add with the numbers and the one that's closest. That's best so far. That's my best so far. And then replace each one until I finally get a set of 4 people that's closest to 1,000 pounds. No. In a declarative system, I could say, here's all my relatives. Here's all their weights. Find me the relatives that 4 of them add to 1,000 pounds closest to that, to exactly hit the limit of weight. For some reason, I want to do that. Bam! It just comes back. The process wasn't there. It automatically came up with that answer. Isn't that amazing? So here's another great example. Oh, by the way, the language that we're going to see as an example, that is Prolog. We won't see that, but that's if you ever see this in the wild. Prolog is the language people often use for declarative programming. And there are subcategories of logic and constraint. Constraint was what we saw in Sketchpad, right? It didn't say, move this thing to make them right angle. It just says, here are some constraints, and zzz, it does it automatically. See, you were already seeing an example in the Sketchpad video of a constraint-based system. I'm going to show you a logic-based system. How many of you have ever seen these logic puzzles? They used to come out of a thing called Games Magazine where you'd have these facts and queries on the facts, right? So here's a great example. 5 schoolgirls take this examination. Each of them, it's actually it's like a race. It's less of an exam, it's a race. And so there's a ranking to the scores they got in the examination or the times on their race. And each girl doesn't want to reveal the exact place they are, so they say one true statement, one false statement, just to kind of be clever about it. So each girl says one true statement, one false statement. And if you work it out, there's only one possible ordering of the 5 girls that has each girl saying one true statement, one false statement, okay? So let's see. So Betty says Kitty was second, but I was third. And one of those 2 statements is true, one of them is false, okay? And Ethel says I was first, I was on top, Joan was second. Can I get that? So each one is talking about the relative ordering of things, but each one of those girls has one true and one false statement, okay? So how does that get solved? Nowhere in the solution did it say how to go about solving it. All it says is here's the facts, but somehow a declarative system could then bubble away, and all of a sudden, here's the answer that comes out. And the answer could be there is no possible answer. Somebody got the wrong thing, and there is no possible permutation of those 4 girls in the order of their finish line of their scores that makes each one of them say one true and one false. So you could have out of this system, it say there's no solution. You could say there's exactly one solution, here it is. You could also say you're under constrained. There are multiple solutions. Okay? So let's see this a demo. So we're going to go to demo mode and watch this live. Ready? Go. Okay. So I'm off camera. Watch this. I'm going to show you something called BYOB. This is basically pre-snap. And there we were trying to convert this over the snap this morning. We had a little trouble. We'll convert this for the final video. But watch this. Here we go. So here it says the following. I'm going to say the following. I'm going to say run. And here is the full screen here. Yoink. Okay. Hi, I'm a declarative programming permutation solver. I can solve any problem of relative position. By the way, beautiful background screen. So as you're making projects, juice them up. Add some background screens as the stage. You can add pictures that you take from your camera. Have the character be you. Kind of make it some fun. Make it fun. So I try to do that here with an actual character that came out of Scratch, but who's a Berkeley student. I don't know how they did that, but they got a Berkeley student in their Scratch repository of images. So she's our main person. I think her name is Melissa, and there's a picture of Cal that I got from the web. All right, so here we go. Okay, type 1 for a simple example and 2 for a more complicated example. So the simple example looks like this. Okay, here's A, B, and C. Okay, here's my simple problem. Here's how I encode simple problem. Check this out. Okay, here's a logic thing. Okay. A, B, and C have some ordering, okay? And it says, in terms of who finished the race first, I say, well, B came in first. B equals 1 means B came in first, right? B is 1. Or B came in second. And false, which is this, not true, or C came in first. Okay? That was my rules in there. And I ask myself, of the ordering of A, B, and C, which of these could actually work in here? We can actually go play with this and see if this works. But that's all I did. I basically encoded the rules. Somebody said that, look, okay, what's going to happen? Either B's first or second, and this false, which is weird, or C is first, okay? And what's the possible solution for that? Let's try it. Okay, I'm supposed to type 1, see if it works. Ready? I'm going to go over here and type 1, run this program, and type 1. Solving it, playing with our constraints. Wait, solving a simple problem. Did I do it right? Let's see if I did this right. Here we go. Stop. Yoink. Okay. Start again. Make sure I get this right. And go. Okay. Type 1. Playing around with the constraints. Okay. And I may have broken it. All right. So demo is good. Good demo, Dan. Excellent. Well done. Let's close this and let's see if I quit this and don't show a demo, if I can finish off the lecture. All right, let's come on back for a second. You're supposed to solve it and do the thing. Didn't work. Okay, that's okay. Things don't work sometimes. We live with that. All right, 3, 2. All right. In summary, we're going to try to summarize what we've seen for the 4 programming paradigms. The one important piece is that most languages are hybrids. Most languages aren't only functional, only imperative, only OOP, or only declarative. They can do all four. And in fact, Snap, the programming language you're working with, can do all four. So it's like, if I say, what does it really feel like? Well, it's like saying, what's the dominant flavor in a fruit juice if you have 4 flavors? Because it's really hard to tell. You can be in Snap and go functional. You can be imperative. You can be declarative. You can be OOP. Okay? So it has all of them. Which is the most powerful is a really important question. I'm going to let you think about that one. Which is the most powerful question of all the 4. Okay? And I'm going to skip this next slide and jump to the conclusion, which is ways to remember the 4 paradigms. Okay? Functional, you evaluate expression and have a result. Imperative, do this, do this, do this, do this. You're allowed to have assignment and mutation in state. Object-oriented says you have these agents, these objects. They're going to send messages back and forth to each other. You either have a factory putting out instances, or you have prototyping where you say, this particular instance is a model for other instances. And declarative is you put facts into the system and you query it for answers, like magic, okay? Those are the 4 ways to remember that. In summary, each paradigm has its benefits. The reason we teach you these is because there's like 4 different tools. It sometimes turns out that the problem lends itself to one of the 4 cases better. Modern languages usually have multiple ones. That's really great. And Snap can be all 4. Thanks so much. All right, folks. We'll see you next time. Thank you for everybody. And I'm going to get this working as we walk it out.